session. We have basically two presentations, myself and Professor Ramesh. So each one 45 minutes slot, each of us will speak for 35 minutes and then we can have some discussions. So with this, I welcome you all to this session. And today, this being a session on climate change and monsoons, I thought we should, this is a work that I'll be describing about some high resolution climate change simulations of the South Asian monsoon in a warming environment. And these are all my co-authors who have contributed, both from India and France. Basically, what I will be showing is the monsoon precipitation over India in the last few decades has shown some interesting changes, some trends, long-term trends. So the question is whether this is naturally forced or is a part of a multi-decadal variability, or is climate change really affecting? This is the problem we wanted to understand. So this is the talk will focus on that. So this is more of a schematic for the general audience, showing the basic drivers of the monsoon circulation. You have the elevated Tibetan plateau, which warms up during the pre-monsoon months. So you have a land-sea contrast between the land and the ocean, which sets up the monsoon circulation. But once the monsoon circulation is set up, the moist winds from the Indian Ocean blow towards the Indian landmass, and so they produce rainfall. So this rainfall also leads to a lot of latent heat release by the latent heat release of condensation, and the feedback between the latent heating and the circulation maintains the monsoon. This is a very simple schematic of the monsoon. And of course, there are year-to-year variations in the monsoon rainfall, which are driven both by internal dynamics of the monsoon system and external drivers like ENSO. So this is a very simple concept of the monsoon. And all India, we know that the rainfall during June to September, whole of India accumulated rainfall for the season mean is about 850 millimeters. And of course, there is spatially a lot of variation along the Western Ghats and Northeast India. These are regions of heaviest rainfalls. And over the eastern part of India, Indo-Gangetic Plain, number of synoptic systems like the lows and depressions, they give widespread rainfall. And areas over Northwest India are relatively much drier. And this is an index of rainfall from all India rainfall from IITM from 1871 to we have up to 2016 now. You can see that all these red bars are the years of deficient monsoon or so-called droughts, and all the green and the blue ones are the wet monsoons. So what you see, many of these red bars are associated with, you can see circles, they are all during El Nino events. So many of the droughts over India have occurred during El Ninos. And likewise, El Nino means a warm phase of the sea surface temperature anomaly in the central and eastern equatorial Pacific. So many droughts over India have happened during El Nino phases, whereas wet periods have accompanied during these cold phases known as La Nina, anomalously cold periods in the eastern Pacific. But you will also see many years which are not associated with El Nino or La Nina. So there is a lot of internal variability in the system. But what is interesting is, in the second half of this full period, if you see, the number of droughts have significantly more in number, compared about 40% more compared to the first half. And so this is something interesting. And we also see that the rainfall has been experiencing a decreasing trend in the seasonal rainfall over India. So this is a spatial pattern of the rainfall from 51 to 2007 based on one of the data sites known as the Aphrodite, which also uses the IMD data. And all this blue color along the Western Ghats and along the Indo-Gangetic Plain, you can see that it has undergone a significant decreasing trend in the rainfall. Of course, there are some pockets where rainfall has also increased, but country as a whole in the last 50 years, the rainfall has declined by about 6 to 7%. And this was a paper in Science by Professor Goswami. They had looked at the daily rainfall over central India, which is well correlated with rainfall over whole of India. What they find is the count of low and moderate rains, that is the intensity between 5 to 100 millimeter per day. Those rainfall counts have decreased, whereas the very heavy rainfall events and the heavy more than 100 millimeter per day or 115 millimeter per day, those intense rainfall events, those occurrences have really, they have increased significantly. So on the one hand, you have the monsoon rains, seasonal monsoon rains decreasing, the low and moderate ones decreasing, and whereas the heavy rainfall ones those events are increasing. And this is not a good news because it can really affect the groundwater and the surface water storage, and because heavy events are going to increase the runoff. So this is not a good healthy signal. So why is this? This is what we'll be examining in this thesis. So this weakening, this decreasing trend in the rainfall is also supported by weakening of the large scale monsoon circulation, which we have. So these are what I have shown is the back trajectories. These are all these various points over India and South Asia. We do a 21-day back trajectory. This is done from May to September every year from 1958 to 2006. And so 21, we try to see where the air parcels are coming from. So you see a lot of particles basically coming from the Indian Ocean, that is the main source, and occasionally particles coming also from northern parts of the Asian continent. So we counted this type of trajectory year by year, and so we made a kind of density of flow reaching the Indian region. And this is a kind of climatological mean density of the flow pattern. You can see the maximum flow comes from the Indian Ocean, which is kind of well known. But what is interesting is, if you look at the density of the flow average over the Indian Ocean region, that flow has significantly declined. So basically what we try to interpret is the decreasing trends in the rainfall, monsoon rainfall, are basically reflected in the weakening of the circulation and the flow coming from the Indian Ocean. And the other interesting thing is, during summer monsoon time, there are a lot of the synoptic systems known as lows and depressions that form in the Bay of Bengal. Lows give a lot of widespread rainfall over central India, and these lows, they generally try to grow through instability mechanisms. They become depression and deep depression, and these depressions and lows, they go west-northwest, giving rainfall along the Indo-Gangetic plain. Typically there are about 10 to 12 depressions every year climatologically, but in the last few decades we see that there is a declining trend in the depressions. Basically the lows are not really intensifying into depressions, and in fact a year like 2010 there was not even a single depression that developed. So this is another important signal that is seen, and recently there was a paper by Professor T.N. Krishnamurthy. He argued that basically the depressions are weakened, the counts are weakening because of enhanced CCN counts, cloud condensation nuclei, and these are basically associated with air pollution impacts over China and India. They have disrupted the organization of convection on the scale of a depression. So the question now we are asking is, so we see these long-term trends both in the circulation, synoptic systems, as well as the rainfall. Is it a climate change signal or not? We know in the last 50 years, the temperatures, last few decades, the temperatures have increased, and basically we also know that the carbon dioxide atmosphere have been increasing during the 20th century. So the question is whether the temperature increase is due to the increasing in carbon dioxide. So recently the IPCC, the last 2-3 reports also said the same thing. The warming of the climate system is unequivocal, and since the 50s, many of the observed changes are unprecedented over decades to millennia. They also said that the warming of the increase in the global mean temperatures are by and large due to the human-induced activity, increase of the greenhouse gases in the atmosphere. And so far the greenhouse gases like the carbon dioxide and methane and other gases like ozone and N2O, hydrocarbons, they have trapped about 3 watts per meter squared radiation because they are trapping the long wave radiation, and carbon dioxide forcing itself is about 1.66 watts per meter squared, and the non-CO2 forcing is about 1.34. So this has led to the increase in the temperatures, global mean temperature. So how do these modeling communities, how did they arrive at these numbers? how do they attribute that increase in CO2 have led to the warming? For this, basically, we use climate models. And when we say climate model, these are basically developed based on these are based on physical principles governing the atmospheric and ocean flows. And these laws, the physical laws, are we have the equation of momentum, horizontal momentum equations, or the Navier-Stokes equation. They are all originally developed by the well-known scientist Isaac Newton. We also have the thermodynamic energy, the equation how energy changes happen. And there is also a mass conservation equation. We have a hydrostatic balance, and we have an equation for water vapor continuity. And then on the right hand side, you will see various terms, Q and F and so on. These are happening on a smaller grid scale, on the subgrid scale. And so these processes have to be parameterized in model. Subgrid scale processes like clouds and rainfall and radiation and turbulence and so on, they have to be described in terms of the large scale variables. And to do this, these equations are basically all the equations of motion, the energy equation. You have to, because these are nonlinear equations, and you cannot solve them analytically. So you have to discretize them. So we break the grid into the sphere into several grid points, and as you make the grid finer, the resolution increases, and then the number of computations are also will increase, and you have different layers in the atmosphere. And likewise, if you have a coupled model with oceans, you also have various vertical levels in the ocean. So typically you end up with millions of computations, and you have a time step. As you make the grid size small, you have something known as the CFL criteria. The time step also gets smaller. So computationally it becomes a challenging job, and so you have to go to supercomputers or high HPCs to solve these climate models, to integrate these models. So basically you are starting with the initial state, you apply a forcing, and then you predict in time. This is the basic philosophy. And as I said, during the last century, the warming is about 0.85 to 0.9 degrees. Of course, it's not uniform everywhere. The extratropics, the warming increases are much more compared to the equatorial region, but planet as a whole has warmed by about 0.9 degrees during the last century. This is the observed temperature. So one of the immediate consequences of the increasing temperature is, as you increase the temperature, surface temperature, the water vapor, holding saturation water vapor pressure increases through what is known as the Clausius-Clapeyron equation. And you can show that for every 1 degree rise in temperature, depending on the mean temperature, background temperature, the water vapor can increase by about 6 to 10%. So immediate consequence is water vapor is going to increase. And so most models project that this is one of the extreme scenarios in the future, known as the RCP 8.5. So this is extreme warming scenario. They all project that under such scenario, because as the temperature increases, there is going to be more water vapor. So it's all going to condense and give more rainfall. So all these models are projecting that, this is again from the IPCC CMIP 5 models. So they are all projecting an increase in the monsoon rainfall. But interestingly, as I said, in the last 50 years, over the Indian region and globally, the temperatures have significantly risen. This has also been a period of warming, but the rainfall has not increased. In fact, it has decreased. So how do you rainfall over India? So how do we explain this? This is the question. So, and the circulation has weakened, the monsoon large-scale circulation has weakened. How can we explain this recent weakening? And so it cannot be purely due to greenhouse gases. And of course, models have their own limitations as well. They come with their own biases. Recently, there was a paper by Sinha et al. They argued that anthropogenically forced changes in the monsoon rainfall will be difficult to detect because there's a lot of natural variability in the system over India. They use speleotherms, which my colleague Dr. Ramesh will be presenting in the next talk. And they argued that this type of what trends which we are seeing in the last 50 years, they have also happened in the past. They have done this based on some speleotherm records. They use the isotopic analysis. And they argued that even in the past, this type of multi-decadal variations have happened. So it's a part of natural variability. So anthropogenically forced signal will be very difficult to detect. This is their argument. Uh, but there's also a different view that the other view is people have argued that aerosols, in addition to greenhouse gases, there are also various types of aerosols, anthropogenic aerosols like sulfates and black carbon and so on. Some of them scatter the radiation and some of them absorb the incoming solar radiation. And the net result is the radiation reaching the surface has decreased. And this can really weaken. There was a study by Chung and Ramanathan. They argued that because of the increase in the anthropogenic aerosols, they have reduced the sea surface temperature gradients in the northern Indian Ocean, and that has resulted in a weakening of the monsoon. And these are the observed trends, and this type of rainfall changes are also seen over the Sahel region and parts of the East Asian region or China. And there was another paper by Bolasina et al. They argued that basically the rainfall decreases which we see in over India in the last few decades are due to anthropogenic aerosols. Basically, the northern hemisphere emissions have increased. So the AOD, the aerosol loading has really led to introduced the interhemispheric asymmetry in the radiation balance, and which has led to the weakening of monsoon. However, interestingly, if you see this experiment, the aerosol experiment, the rainfall reduction, what they see is not just over India, they are getting all over Asia and China. Interestingly, if you see in the observations over eastern China, rainfall has actually increased. So, although they indicate that aerosol could be a forcing, there are some differences in the model simulation. Also, the precipitation decrease in the observations which you see over west coast of India is not correctly reflected in their aerosol run. So, there are issues again, and but there is a kind of emerging consensus that anthropogenic aerosols have a likely role in the observed decreasing trend. Various studies have shown, and various physical mechanisms have been proposed. One is through the reduction of the solar insolation at the surface, known as solar dimming, and this can reduce the temperature gradient in the Bay of Bengal and over the northern Indian Ocean, and reduce the convective activity. And there are also a view that it is not just over India, it's a more of a continental scale, large scale cooling over the northern hemisphere by the sulfate type of aerosols, and which can weaken the monsoon. This was by Bollasima. And there is also a paper by Ganguly et al. Who argued that aerosols, they try to decrease not just the surface temperature gradient, but also the tropospheric temperature gradient, and weaken the vertical shear of the monsoon. And interestingly, some of the aerosols like black carbon, which are trapped in the first few kilometers, first 2 to 3 kilometers above the boundary layer, because they absorb the solar radiation, so they warm the layers above the boundary layer, whereas below the surface the temperatures are reduced. This leads to what is known as an increase in the static stability, and the increase of static stability by solar absorption can weaken the circulation. And there is also a reduction in the temperature at the surface cooling. And also when you cool the surface, it can also lead to decrease of water vapor availability. So various mechanisms have been proposed. And so on the one hand, we have the GHGs which are trying to increase the temperature, increase the water vapor holding capacity, and lead to more rainfall. On the other hand, the aerosols are trying to compensate it by trying to bring down the solar radiation at the surface and trying to reduce the rainfall. So there is a kind of tug of war between these different forcing elements, between the greenhouse gases, aerosols, and other changes. So we did this experiment study, which was later on reported in Nature News and Views. And I'll be basically talking about this. How do we decipher the desiccation trend of the monsoon rainfall in a warming world? So what we did was we basically used a global model. The interesting, although it's a global model, over India, over South Asia, and even a wider region, we applied a very high resolution zooming. So the grid is not uniform. Over this zoomed region, the grid size is much smaller. It has a high resolution of about 35 kilometers. And as you go away, the resolution gets coarser. So the advantage of having this zooming is you will be better able to resolve the orographic effects, also the regional forcing like the aerosols and the land use changes that have happened. And And interestingly, this model, the global rainfall distribution as well as the global monsoon circulation as well as the regional scale features are much better resolved when you have this zooming. So the zoomed version shows much more rainfall over India as compared to the no zoom run, which was a 1 degree by 1 degree or a 100 kilometer by 100 kilometer, which is relatively drier. This is a mean monsoon rainfall. The zoomed one, the rainfall distribution, you can see the improved rainfall along the Western Ghats and Northeast India and also over the Indo-Gangetic Plain. The top one is the observation. And interestingly, when you improve the rainfall simulation, the Somali jet or the what you see over the Arabian Sea, that also intensifies. So it is telling that basically the precipitation and wind, they are constantly interacting. So this is one of the good models. And we said that why not use this model to make some climate projections and also try to look at what has happened in the historical period during the 20th century. So we had two experiments. One is the historical run, which includes natural forcing. By natural, I mean solar irradiance changes at the top of the atmosphere, volcanic changes, and anthropogenic forcing due to greenhouse gases like carbon dioxide, aerosols, different types of aerosols, land cover changes. And this was a 120-year run. It took us a lot of time, more than 2 years to complete this run at this very high resolution. And we also have a experiment with only natural forcing. There are no anthropogenic forcing. So if you this is known as the historical natural. So by comparing the historical and the historical natural runs, you will be able to understand how much the anthropogenic influences have affected the monsoon. And we also make a future projection following one of the scenarios known as a RCP 4.5, which is a kind of moderate scenario where the radiative forcing at the top of the atmosphere reaches about 4.5 watts per meter squared by end of 21st century. And all these runs were made using the LNDZ model, which I discussed earlier. And these are basically atmospheric model runs where the sea surface temperature, which is used to force these models, came from the coupled model run, the original IPSL coupled model. And we also had a run only with greenhouse gases. So there was no aerosols and land use change, only GHG forcing. Like carbon dioxide. And what we see is when you compare the surface temperature simulation in the historical run and then the future is continuing RCP 4.5, the yellow is the natural line. You can see the warming temperatures clearly attributable to this, a very significant warming that has taken place in the 20th century. You can associate with the anthropogenic influence, and you also see those warming trends over India, and which is projected to increase in the future over South Asia. But interestingly, when you look at the rainfall during the June, July, August, September season, what you will find is this black line is the observation from IMD data set. You can see a decreasing trend in the rainfall. This is the Pi et al. IMD data set, which is about 7% decrease. Our historical run is the brown line, which is also showing a decreasing trend. But you don't see a decreasing trend in the historical natural experiment, that is the blue line, which is showing this decadal and multi-decadal variability, but there is no clear trend. And what is also interesting is the rainfall is projected to decrease. We had only one realization in the 21st century, at least in the first half of the 20th century. The advantage of using the high resolution model is the mean rainfall is somewhat very closer to observations. But if you look at all the IPCC models, the CMIP-5 models, the mean is nowhere close to that. It is far, far underestimated because of the coarse resolution. And there is a lot of spread among these models. There are about 35-40 models. There is a lot of spread. And in fact, it shows a slight increasing trend in the mean rainfall over India, as I told, because of the increased water holding capacity. So interesting, what the point is I want to say is the historical simulation captures this decreasing trend, although it is somewhat more exaggerated in the model. And the other thing is the use of high resolution. We counted the heavy rainfall events from the daily rainfall over central India, same region of Goswami. We see that just like the observations, the historical run shows that the increase in the heavy rainfall, whereas the mean rainfall is itself decreasing, and it is further projected to increase in the future, but you don't see those in the natural run. And we have tried different convection schemes to see whether this is a robust result. Is it sensitive? We see that no matter you change the choice of the cumulus convection for representing clouds, whether it's two different, we do see a decreasing trend, which you don't get it in the historical natural using the same convection schemes. And whereas the frequency of heavy rainfall increases irrespective of the choice of the convection. And when we look at, this is the attribution we did, you take the difference between the historical minus the natural for the last 50 years, you can see all these red areas with the dots, which is basically a statistically significant areas along the Western Ghats, along the Indo-Gangetic Plain, a decreasing trend in the rainfall accompanied by a weakening of the monsoon flow. You can see an anomaly, easterly anomaly, indicating that the southwesterly flow has weakened. And you also see interesting changes, consistent changes over Sahel and over China. And over Eastern Indian Ocean, over the equatorial Eastern Indian Ocean, precipitation has increased, actually increased, shows an increase in this experiment, which I will come. But when you do only a GHG forcing experiment, only with greenhouse gases, without any anthropogenic aerosols and land use change, the rainfall actually intensifies and the circulation strengthens. So we rule out the possibility that this decline is because of the greenhouse gases. It is because due to the other regional elements like the aerosols and the land use change. And during the last couple of centuries, significant land use changes have happened over South and Southeast Asia. About 40 to 45%, there are publications telling that about 40 to 45% of forest cover has been replaced by agricultural land during the 18th and the 19th centuries. And it has also continued in the later part. And these publications are there. And these data sets have gone into the forcing. The other thing is the anthropogenic aerosols, both the scattering and the absorbing type. So there is a reduction in the radiative forcing due to the aerosol at the top of the atmosphere, and there's an increased absorption. You can see over Indo-Gangetic Plain and over China because of a lot of pollutants. And the other important signal is there is a very strong pronounced warming of the equatorial Indian Ocean. It has warmed by about 0.5 to 1 degree in the last 50 years or so. So these are all important signals. So on the one hand, what we are finding is because of the increase in the crop fraction as compared to the tree fraction, the planetary albedo in the model simulation has increased by about 9 to 10%, that is shown in the green line, just over India. And whereas the warming of the equatorial Indian Ocean has happened by about 0.5 to 1 degrees, and the anthropogenic aerosols have largely dominated the Asian region, the South Asian region, since the 60s and the 70s. So, because of the increased albedo, we are losing a lot of radiation back into space. So, that has to be compensated by increased subsidence. So, we find in the simulation that sea level pressure increases over India, both in the model and the observations. But because of the increase in the temperature, the water vapor itself has increased over model, in the simulation, and projected to increase. But there is a lot of subsidence happening over India. And since the monsoon has weakened, when you look at the winds at the lower level and the upper level, you have a strong shear. In the upper level, you have strong easterlies, winds coming from the east. So this shear is a measure of the intensity of the circulation, monsoon circulation. That shear, easterly shear, has actually weakened. So as the rains decrease over India and as the temperatures are increasing, we find that there is a decrease in the soil moisture in the model simulation, which is projected to continue into the future. So because of the warming associated with the equatorial region, associated with sea surface temperature, there is more convection, more upward motions over the equatorial region, which is trying to produce descent over the Indian landmass. So basically the monsoon overturning Hadley type of circulation has weakened and is also projected to weaken in the future. And so we are seeing the response to the aerosols, the land use change, the SST warming, they are weakening the overturning circulation. But once you decrease the rainfall over India and weaken the convection, much of the circulation in the subtropics and the extratropics, which are associated with the cold westerlies, they try to intrude southward and they can produce very large scale continental scale patterns. You can see that there is a large scale cooling of the troposphere in response to the weakening of the convection over the Indian region. So you have warmer temperatures in the equatorial region and cooler temperatures in the troposphere over the high latitudes. So these are all various feedbacks that are happening. So the main result what we find is when you compare only the greenhouse gas experiment and the historical experiment having the land use and the aerosols, what we find in the greenhouse GHG only experiment, both the moderate rainfall events over central India, 5 to 100 millimeter per day, as well as the more than 100 millimeter per day, those type of events, they tend to increase. You can see this is all relative to the historical natural experiment. Whereas in the historical experiment, we find that the heavy rainfall events, more than 100, they have increased at the expense of the decrease in the moderate rainfall events. So these two categories are very distinctly different. And this is telling the importance of the non-GHG forcing elements. So basically what I want to summarize is, we have looked at the long-term climate change. We did some modeling experiments using a high-resolution model, looking at the monsoon precipitation changes during the decreasing trend in the monsoon rainfall and the increase in the heavy rainfall event occurrences. And we are attributing this to regional forcing, the aerosols, land use change, and the equatorial Indian warming. And because of the use of the high resolution, it's a big, all the second order moments are better captured. A robust increase in the frequency of heavy rainfall occurrence are seen in the climate change simulation. And the role of aerosols in the weakening of monsoon, it's now there's an emerging consensus from different groups. Of course, the monsoon has a strong internal variability over the South Asian region. So it is necessary to have multiple realizations to better quantify the aerosol impact on precipitation. We could not separate the effect of aerosol and land use change, which we are trying. The Indian Ocean warming signal, this problem is not well understood. Our own impression is that my colleague Dr. Roxy Native at IITM has also shown how this Indian Ocean warming can weaken the land sea contrast, and it can have an impact on the monsoon. But weakening of the monsoon circulation itself can reduce the upwelling in the equatorial Indian Ocean, large part of the Indian Ocean, which is coolest during the summer monsoon time. And that can contribute to this warming. So it's still an open problem, and that needs further studies. And we have used basically a standalone atmospheric model, but we will need a coupled model to better comprehend the aerosol forcing on the South Asian monsoon. So what is the way forward? At IITM, we have developed an Earth system model, a fully coupled model. It's not just atmosphere, ocean. It has an interactive cryosphere and a biosphere. And we will be participating in, and this model we have also improved the radiation balance, this global mean temperature. And the latest version, the ESM2, the monsoon rainfall over India has significantly improved because of the use of a new convection scheme. And it also captures many of these disturbances that form in the Bay of Bengal, synoptic scale disturbances. So we have started the CMIP runs, and this model will be contributing to the IPCC, the first from India. So we want to look at this problem, and we have also introduced aerosols in the model. We will be looking at all these aspects in this model, and with this I want to end my talk. Thank you very much.